Hey guys, it looks like it's working. Do you guys have any questions for me so I can start reviewing? Sorry that that wasn't working for whatever reason. It looks like it's working. Let's see. All right. So you should be able to type into the chat window, and I'm getting my chat window up now so I can see what you say, so I can answer your questions. All right, so it should be working. Makes me very happy. All right, I have my comment section up on my other computer, so if you could just type in the box that you're watching, that things are working, that would be great. Hey, who's here? All right, I got a few people watching, which is good. I just don't know who you are and what help you may need. And Matt, I really like the idea of giving you all 100, but unfortunately I cannot do that. So you need to earn that 100. But thank you. All right, guys, let me know what you want me to go over. All right, any questions, guys? Any at all? I'm waiting. All right, I'll get some questions here myself. All right, so first I'll tell you what is going to be on the test. You should know because it's in your notes. But let me screen share with you guys. So let me go into my bonding notes. So the first page of your bonding notes tells you everything that will be tested. Not so much about chemical and physical properties, like in this first bullet here, because that's the next unit. But you know some physical and chemical properties already. You do need to know what an ionic compound is and a covalent compound. That is something that we've been going over for 2 units now. You need to know the difference. At this point, I can't go over it, again. But I will, because I'm a very, very generous person. So, all right, ionic compound, metal, non-metal. Covalent is non-metal, non-metal. Okay, stop sharing that for a second. All right, so ionic, metal, non-metal. Covalent is non-metal, non-metal. Another name for covalent we call molecular compound. Let's see, Lewis dot diagrams for covalent and molecular compounds. Just remember, covalent sharing means caring, right? So they share their electrons. That's why we count up all of the valence electrons and we distribute them around. Ionic is a transfer. So that's where we have the brackets that come in and the charges. So an ionic compound like KCl. Okay, how do I know it's ionic? Potassium is a metal, chlorine is a non-metal. So they're going to transfer electrons. So one of them likes to give up electrons. You should know that a metal likes to give up its electrons. So you'll have 1 valence electron for potassium because it's in group 1. And then you'll have 7 for chlorine. Okay, so chlorine is not happy because it doesn't have 8. And potassium's not happy because it's stuck with this 1 in its last shell. So there's one thing that I'd like to show you. It's let's see. It's the electron configuration for potassium. So I'm going to go find that. Chemistry reference tables. There it is. Okay, just bear with me 1 second. All right, so potassium is 2,8,8,1. Okay, so if it gets rid of that last electron, it's now 2,8,8. It's happy. Okay, and that's something that I kind of assume that you got, but you need to understand why it needs to get rid of that 1. Once it gets rid of the 1, it's now 8 in the last shell instead of the 1. All right, so it's going to transfer that electron over to chlorine. And I like to draw the arrows. The final answer for dot diagram would be K with no electrons. They've been given away to chlorine. And now it's a +1 because it's lost a negative electron. And chlorine will be completely full. And the X is fine. You can have a dot there, but the X tells me that that electron came from the potassium ion. And you need to remember that this is a -1. Now, a common mistake is when we have something like CaCl2, where we have 2 chlorines. So calcium has 2 dots. Cl is going to have the 7 that we just did before. Okay, so it has a 7. Let me move this up a little bit so you can see. It's all there. So this electron comes over here, and this one will come over here to fill it. Now, when you write it, this is a +2. You all seem to understand that. But when we write the Cl, you put the 2 in the front. That means you have 2 of them. The Cl needs to be completely filled. And here you can have that X. This is a -1. That means that each chlorine is gaining 1 electron. Okay, most of the time I'll see this as a -2. Okay, you can't have it as a -2. Okay, it must be a -1. You account for the charges with the 2. Okay, so it would be +2 plus, you have 2 chlorines that are a -1 charge. Together that equals 0, and that's what you want. You want it to be neutral. All right, so that's a dot diagram for an ionic compound. Covalent compounds share their electrons, as I said before. So let's think of something that we can draw. We've drawn so many of them. Let me draw another bent structure. So water is bent. There's one other one that's always bent, and you'll see this one pop up on the reagents every now and then. So that's SO2. Am I right there? No, sorry. It's H2S. Okay, it looks just like water, except you have a sulfur in there. And sulfur and oxygen are pretty close to fluorine, so they're electronegative. So they'll steal they all want to steal the electron from the hydrogen atom. So to draw this, we need to count up all our electrons so we can share them. So I have 2 of them. They are 1 each for hydrogen, and you have 6 for sulfur. So that's a total of 8. So we put the one that's unique in the middle, which is sulfur, and then we put the H's next to it. Now the reason I put them like this is these lone pairs of electrons are going to repel the bonding pair. Electrons are negative. Okay, because of that, they're going to push away, and it makes this bent structure. Okay, so a bent structure means it's a polar molecule. Okay, there's 2 things that you might I don't want to say screw up. You might mix up. It would be polar nonpolar bonds versus polar nonpolar molecules. Okay, so a bond is just the bond between 2 atoms, and a molecule is the entire thing. So it gets a bit confusing. If it's CH4 methane, okay. This is a bond between the carbon and the hydrogen. The entire molecule is everything in the molecule. Now that's easy to see here, but when you get to something like, let's put it here, N2, this is the one that has a triple bond between them because it's nitrogen. When you have something like this, it's hard to see the difference between a bond and a molecule because there is no difference. So this is the bond right here in the middle here, but the molecule is the entire thing. So the bond between a nitrogen and another nitrogen, the polarity is based on electronegativity difference, but they're the same. So a number minus the same number is going to be 0. When you have electronegativity difference less than 0.4, it's a nonpolar bond. Meaning no one's pulling more than the other. They're equal forces. Think of it as tug of war. This one's pulling a certain amount, this one's pulling the same amount, so they're not going to go anywhere. So that's equal sharing, nonpolar bond. When you look at the entire molecule, that's where we use SNAP. SNAP tells me if the molecule is polar or nonpolar based on symmetry. So if I draw a line down here, everything on the right is the same as everything on the left. So this is a nonpolar molecule as well. Okay, all right, so there's one good question that I'd like to work on with you, okay, from the packet. So let's see if I can get this on here. Yeah, you can kind of see it, it's backwards, so. All right, let me see if I can type it on here. Let me screen share with you. I don't have the packet with me, but I can type it up quick. All right. So look at the following electron dot diagram below. Okay, and the dot diagram is hydrogen fluoride. So let me see if I can find that real quick. And that. I saw it. There it is. Where did it go? Oh, it's almost better to draw it sometimes. All right. That's not what I want. Okay, so we're looking for the thing that's on the right here. All right, so look at the following electron dot diagram below. Hydrogen fluoride, this one on the right. The electrons in the bond between hydrogen and fluorine are more strongly attracted to the atom of, okay, so the electrons in the bond are more strongly attracted to which atom? That's what it's asking. All right, so your choices are either hydrogen or fluorine. Okay, and what are you going to say? You're going to say it's definitely fluorine. Why? Because fluorine is more electronegative. But what does electronegative mean? Strongly attracted to electrons. So fluorine's going to pull the electrons towards it. You can actually see that in the diagram, right? Fluorine has all of the electrons around it. And then the other part is the reasoning. So it's fluorine because it has a higher electronegativity. Okay, so that's my first question. Second question. 2. Which type of bond is formed between two chlorine atoms in a chlorine molecule? All right, so what do you think? So it's two chlorine atoms. Chlorine is a nonmetal. So this makes it a covalent bond. But there's two choices here that are covalent. There's polar covalent and nonpolar covalent. And I just did this with you. So if they're the same atoms, their electronegativity difference which I like to abbreviate as END, is 0, which means no one atom is pulling the electrons more than another. Therefore, it's nonpolar. There's no pole. Okay, and then let's see the third one. Which diagram best represents the structure of the water molecule? So water is bent. Just like I showed you for H2S. The other thing to remember is that there are 2 hydrogen atoms and 1 oxygen atom. A lot of the times I'll see 2 oxygen and 1 hydrogen in the middle. So it'll look more like, let me show you. It'll look more like, I can't even proper. I'll see this, okay? That is, it doesn't exist, first of all. That's HO2. That's not H2O. Okay, so don't do that. Okay, make sure that you are accounting for all the atoms that you have. Okay, so that was one question that a student had from the packet. Do you guys have any questions for me? Let's see what else is on your test. You have types of reactions on your test too, and I can show you that again. Right, so screen share again. Right, so types of reactions, here they are. Okay, so synthesis, you have one product. You are making something. And that something is one thing. So you're taking 2 things, putting them together, and you're making one thing, which is a compound. Decomposition is the exact opposite of synthesis. You're breaking them down. So you start with one thing, and you're decomposing it into its parts. So I can show you this for 1 second. Right, so the way I can show you this is H2 plus O2 goes to H2O. Okay, what type of reaction is this? It's a synthesis reaction. Okay, we know it's a synthesis reaction because you're putting 2 things together, hydrogen and oxygen gas, and you're making water, you're making one product. Decomposition of this would be H2O, one reactant goes to H2 and O2. It's the exact opposite reaction, but you're breaking it down. You broke the hydrogen out and you broke the oxygen out. Now, not every time is there one thing here and you're making 2 things, but you need to recognize that you're breaking whatever compound you have down. Another reaction that seems to be confusing is a single replacement reaction. So let me get that picture up. So single replacement. I have one here. So Al, CuCl2. And if Josiah is here, he's going to be mad at me because I didn't balance it. So let me balance it. And it goes to 2AlCl3 plus 3Cu. Okay, so that's the whole thing. How do I know this is single replacement? Because one partner's coming into the mix. You're swapping this person out, this copper, for an aluminum. And now you make aluminum chloride, because now aluminum replaced copper, and you're left with copper. Okay, another way to recognize it, element, compound, new compound, and another element. Okay, now I put that there because when you get to double replacement, so this is single. When you get to double replacement, let me find it going. BaCl3 plus Na2SO4 goes to Na2 Cl plus barium sulfate SO4. Okay. Oh boy, this always seems confusing, but double replacement. One way, and I don't want you to rely on this, but it's the most complicated formula that you've seen, or the most complicated chemical reaction that you've seen. So barium is going to replace your sodium, do-si-do, right? They swap positions, and then chlorine and SO4 also swap positions. So you're replacing two things. So it becomes barium sulfate, so Ba sulfate, that's what I see here, and sodium chloride, NaCl salt. Okay, compound, 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 but it's new, and compound, and it's also new. Okay, so how's that different than single replacement? Single replacement has two elements in it. Okay, so you start with one element, you end up with a new element. Okay, and here in double replacement, it's compound, 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 compound. Okay, double. Okay, any other questions? No? All right, what else is on your test? Let's go see. All right, so dot diagrams, covalent, ionic, we did. Polar covalent bond is unequal sharing. So you end up with a pole. Nonpolar covalent bond is equal sharing of electrons. It's all of the diatomics. Metallic bonding is a sea of mobile electrons. This is such an excellent review sheet. I suggest you pull this out tomorrow morning or during the day before your test, so you know what you're talking about and you know what you're not getting. Okay, we talked about exothermic and endothermic reactions. They are on there, but it's not so much me calling them exo or endothermic, but you're going to get questions about breaking bonds and forming bonds. So remember BARF, which is such a great thing to remember. But when you break a bond, you absorb energy, so you have to take in the energy to break it. When you form a bond, you release energy. Okay, so what that looks like. That means where the energy is. So let me think of one. Okay, so you guys remember good old ATP? ATP. All right, and ATP is full of energy. So when you break it down into ADP plus another P, right? Because the T means try and the D means die. So 3 phosphates, 2 phosphates, plus 1 phosphate. Okay, so this is a decomposition reaction. So you're breaking a bond. So when you break a bond, you have to absorb energy. BARF. Okay, so this is absorbing energy. Okay. When you form a bond, you release energy. So they're going to ask you questions. They'll show you formulas. They'll ask you what it means. They'll ask you if it's breaking, if it's forming. So if it's a synthesis reaction, like this guy, you are forming a bond. Remember BARF. BARF. Okay. So when you form a bond, you release energy. Decomposition reaction. When you break a bond, you have to absorb energy. Okay. And you should remember when you're absorbing energy, it's endothermic. Exothermic is a release of energy because exo, exit, energy is leaving. Okay. All right. Let's go on. What else do we have? Okay, atoms bond together to obtain a total of 8 valence electrons to become stable. And there is an exception for that one. Hydrogen only needs 2 valence electrons. Noble gases have a stable valence configuration. Remember, they're group 18, so they have 8 valence electrons, and they're happy. So they tend to not bond. They associate only with themselves. They're loners. Hydrogen bonding, you need to know intermolecular forces. So intramolecular forces are ionic and covalent bonding. That means within the molecule. So when you're talking about water, it's H to O, that bond. But intermolecular forces mean from water molecule to the other water molecule. Hydrogen bonding will occur between water molecules because it's the hydrogen of one water molecule with an F, O, or N of another molecule. So if it's water, it's hydrogen of one water molecule bonding with the oxygen of another water molecule. Remember, hydrogen bonding are the strongest intermolecular forces that there are. Because of that, they have a high melting and boiling point. We'll get to vapor pressure at a later date. All right, so they will boil at a much higher than expected boiling point because this is covalent. And what you should remember is the properties, right? So ionic has a high melting point, covalent has a low melting point, except when it has hydrogen bonding between molecules. So hydrogen to oxygen of a different water molecule, nitrogen to the hydrogen of different ammonia molecules, and hydrogen to fluorine of different different hydrogen fluoride molecules. Dipole forces are polar molecules like the ones that we've seen before. So carbon tetrachloride, so CCl4. That was not that's not one of them. So dipole is when you have a polar molecule. It's strong. It leads to higher melting points. They are soluble in water, but they're not as strong as your hydrogen bonding. Then you have these other weak intermolecular forces. It's all nonpolar molecules. It makes them insoluble in water, and they have very low melting points. So this is a typical covalent molecule. You should remember that Lewis dot is 1 valence electron, so you already know that. For compounds, you must get the formula first, and that's a big one. So if they ask you for like magnesium oxide, you have to draw out the formula first. You have to do crisscross reduce and figure it out. And I can do that with you in a second. This review sheet. You have a review packet from class that I gave you. You have 2 review packets. You also have this review sheet that I'm going through, the key ideas. It's the very first page of your bonding notes. So this is there. Let's see. Most polar or most ionic is going to be the largest electronegativity difference between atoms. Least polar or least ionic is smallest electronegativity difference. If they ask you a question with both ionic and covalent bonds, that's a polyatomic ions. Because if you have, right, I can do that. Let me show you. Okay, so if they ask you a question, they give you like NH3. I gotta get my chemistry reference tables. Hold on. Always need your reference tables. I don't have mine, sorry. All right, electronegativity, that's what we need. All right, so if they ask you which one's the most ionic in character, and they give you the choice between NH3, actually, no, they wouldn't do that. Most ionic character has to be an ionic compound, so let's do that. So KCl, my personal favorite, and calcium chloride. Okay, if they ask you which one's more ionic, it has to do with the electronegativity difference. So if you're more ionic, you have more of a difference between your electronegativities. That makes sense because you're more likely to be an ion. Okay, so you go to table S. Don't guess, go to table S. All right, so let me do that. Okay, so KCl, that's the first one. So potassium. Where are you, potassium? Okay, electronegativity 0.8. Chlorine, 3.2. That's pretty big. And then calcium, 1. And chlorine is the same. Okay, so let me stop sharing and come back. All right, so you got to do the difference between these two numbers. 3.2.8 is a bigger difference than CaCl. This would be a 2 here. Because, you know, 0.8 to 3.2 is a bigger difference than 1.0 to 3.2. Okay, so that means KCl, more ionic. Okay, the same thing applies for when they give you covalent molecules. So which one's more polar in that instance? Because, you know, you can be polar or non-polar. You can never be ionic if you're a covalent molecule. So yeah, there's that. I think we're good. I think I got everything. Unless you guys have questions for me, I think we are done. Let me see where we are. So yeah, we got all these things done. Maybe polyatomic. Let me show you that. Okay, you remember polyatomics? Let's find a good one. Sodium hydroxide, NaOH. How do I know it's polyatomic? It has 3 elements. 1, 2, 3. Okay, so OH is found on table E. That's what that tells me. So sodium is 1 element, oxygen is another, and hydrogen is another. Now, when they ask you what molecule has an ionic and covalent bond, it's going to be a polyatomic ion every time, because this O to an H is a covalent bond. But this Na to the OH total is an ionic bond, because Na is a +1. Do you remember writing formulas? And then OH, I get from table E, is a -1. So this whole thing acts as an ion, even though oxygen and hydrogen are covalently bounded to each other. So you get both bonds in a polyatomic ion. Okay, and I think that's it. I think I am done. Okay, so let me see. I think I did everything. Let me just make sure. I did these. Did barfing, we did snapping. Yeah, no. Maybe metallic bonds. You need to know that there are a sea of mobile electrons. That's what accounts for its its ability to conduct electricity. Okay, so the mobile electrons are free flowing because they like each other. So they're always moving around. So if it's a gold ring and it's all gold, there you go. Let's see. Oh, okay, let me answer. Yes, tomorrow's exam will be the double periods, just because we have a working day. So I'll break up the exam into part 1 and part 2. So later on in the day, since the periods are not together, you'll take the part 2, like the written part, the dot diagram part, to do that. Part 1 will be multiple choice. So the first period that I see you, which is period 8, because tomorrow goes 1, 2, 3, 8, 4, 5, etc. All right, let me do some dots, because we love dots. Let's do more dots. Dots for everyone. Dot diagrams are the best diagrams. All right, so let's do ionic. Let me stop sharing. Okay, so I had the ones on there, which would be good. So let's do KBr. Oh, this marker broken. Next marker. Okay. All right, number 1, KBr. Okay, nice easy one. All right, so this is an ionic compound. So when you draw this, you need to make sure you have the ion. So that means the brackets. So it's K with a dot, right? And then you have Br, which is group 17. So you have 3, 4, 5, 6, 7 electrons. This one will come over here. This becomes K plus 1 because it's metal, it loses the electron. And it goes over here to Br, boop, 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 X. Okay, so you don't have to have the X. I like to have the X because it tells me where they went. Okay, so I kind of skipped a step here because I knew that it was KBr, but sometimes they just ask you for, they just go, what is calcium oxide's dot diagram? And you need to know how to do that. Okay, so they'll give you the name and you got to do it. All right, so calcium oxide, there it is. You got to write the formula. So Ca plus 2, O minus 2. Crisscross, it becomes Ca2O2, but then you reduce it. CaO. Okay, calcium has a plus 2 charge. Oxygen has 6 valence electrons, so it needs both of them from calcium. So this becomes Ca plus 2 oxygen minus 2. That's that. Okay, is that good with ionic? I think we are. All right, covalent. So if these are all ionic, okay, so they transfer electrons. Okay, covalent equals sharing. Sharing. Okay, you may be asked to draw a dot diagram similar to this one. So carbon tetrachloride. Very special. All right, so you need to figure out how many dots you need in total because you need to share them. So carbon is 4. You have 4 chlorine, which is 7. 32 is total. Which one's unique? It's carbon. He's all by himself. He's going to be surrounded by 4 chlorines. I like to bond all mine together first. So all chlorines attached to the carbon. That counts for 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Done. Ta-da! Ta-da! That's it. Now, carbon chlorine, that's a bond. Is it polar or non-polar? How do we know? We go to periodic table, table S, we do electronegativity difference. This is a polar bond. Okay, but the entire molecule depends on SNAP. Okay, so this is a tetrahedral. Everyone is sharing equally. So this is non-polar molecule. Okay, so that is totally possible. So you can have a non-polar molecule, the total thing, with polar bonds in it. It's just they have to be equal. So this chlorine pulls this way, this one pulls that way. They cancel out. This chlorine pulls down, This one pulls up equally though, so they cancel out. Everything is symmetrical. There's a chlorine here, there's chlorine there. So if I fold it over, they're all taken care of. Okay, that's carbon tetrachloride. The one that always gets you guys confused are the double, triple bonds. So CO2 always gets you guys. And what's the other one? It'd be NH3. No, it'd be N2. You know, O2 also does it. Okay, so let's do CO2 first. So it's 4 plus 12. So you have 16 electrons that you need to share. Carbon goes in the middle because he's unique. Okay, we bond these together first. 4. Oh, the shapes. We'll do that in 1 second. Okay, so this one's tetrahedral because it has 4 things attached to it. That's why it gets the prefix tetra. So 4 things attached, tetrahedral. That one's symmetrical. They're also in your notes, Nicole, so you can look there. And I set them up based on polar and nonpolar. This one, CO2, since it's straight across, that one's linear, like a line, straight. H2O, that one has the 2 lone pairs, and the 2 lone pairs push away, so it makes this one bent. And that one's polar because it's not symmetrical. NH3. Has 1 lone pair up here. This is pyramidal. Okay, that one is not symmetrical either. Yeah, and you have the linear one, which is CO2. Most of the molecules are going to be linear, but you do have the weird ones like tetrahedral. CH4 is also tetrahedral because you have 4 hydrogens surrounding carbon. Once you get the lone pairs, that's when things get polar because they're not going to be equal charges in charge distribution. All right, back to CO2. Okay, so I have 16 electrons that I need to share. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Uh-oh, fellas. All right, so we got to fix this. So these, I'm going to bond here. And, oh, you know what? I don't like that. And then this one is going to come over here. So you create double bonds. That's really what's going to happen. No, we can kind of keep that. Okay, so we get the carbon in the middle. We get the oxygen here. Okay, and we get these double bonds. Now, carbon's happy. Carbon has 8. So you're going to leave them alone. So 8, 9, 10, 11, 12, 13, 14, oops, 15, 16. All right, so we got an issue. So you need to we need to get this one over here. And we should be good now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Hooray! Everyone's happy too. Okay, that one's linear. Okay, that one's symmetrical. O2. O2 is 6 plus 6 equals 12. Oxygen. And remember, oxygen likes double bonds. So 1, 2, 3, 4. We'll start there. 4, 5, 6, 7, 8, 9, 10, 11, 12. Happy. Okay, so you have a double bond in the middle. Another way to represent the double bond, we got the double bond, and then those other electrons on the side. Okay, N2, also linear. Okay, we're going to have only 10 electrons to share. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, no, we're not happy. All right, so we're going to take these, bring them down. Okay, so let's see if that works. Make a triple bond because it's nitrogen. He likes to have triple bonds. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. That's that. He's happy. Okay. And this one's linear. All right. I think we're good. It's up to you guys. Okay, and remember you do have your review sheets that I gave you, and I put the key on Google Classroom, so you can always look there too. Don't stay up too late studying. I just want to point this out again to you guys, the electronegativity difference. You have nonpolar, you have polar covalent bonds. Do you see the difference here? So if it's greater, if the electronegativity difference is greater than 0.4, it's polar, okay, as long as it's a covalent molecule. If it's an ionic molecule, it's greater than 1.7. Okay, you should be able to tell the difference between covalent and ionic without doing the electronegativity difference. Okay, metal, non-metal, non-metal, non-metal. Okay, when is the latest we can do the CASEL learning? I take it right up until the test. So you can do it period before, but once I give you out the test, that's it. So tomorrow you have until period 4 essentially, because we're going to start the test right after period 3 because of the early release. Okay, and you know, here on your notes, I have calcium chloride. I have another ionic diagram. So you can show it this way, where you have the charged ions that are the same opposite each other. Okay, which is correct. Or you can put a 2 in front of the chloride like I did before, and that's correct too. Either one. Okay, sharing. All right, so water, I showed it this way, but now you know once you get to molecular shapes that this is really a bent molecule. It's not linear, which makes it a polar molecule. You need to know that. Okay, here are I think we have the shapes coming up. Polarity. Okay, so linear, here we are again. This is CO, carbon monoxide, H2O, bent, and then pyramidal with the lone pair. So you see there's 2 lone pairs, and here now there's 1 lone pair. So once you have that, you have a problem. I know I said linear is symmetrical, but there can be asymmetrical linear. Like if you're looking at this is not the same because you have a carbon here and an oxygen here. If it was carbon-carbon, that would be a totally different story. But the oxygen pulls the electrons closer to it, so that makes it a polar molecule. This one's linear and symmetrical because when you fold them over, everything is the same. Here's CO2. Tetrahedral is also symmetrical. And then we have this little table that summarizes everything. Carbon tetrachloride. Here's H2S like I showed you before. It's just like water. It's bent. Okay, intermolecular forces. So you need to know hydrogen bonding is between hydrogen and FO and N. Remember, H bonding is FON. And that is that. I think we're good. So I'm going to sign off because it is 10 to 9 and that's my bedtime and I have some other work to do. So good luck. Come and see me in the morning if you have any other questions that I haven't answered. Have a nice night, guys. Thanks for coming.